All right, so in 18, one of the things that we had found was we had a new formula for finding our electric field. Okay. So the original definition was it was the electric force per charge. And we talked about using test charges and, determining the force on the test charge and then dividing by the charge to get the value for the field. And if we had a point charge, then we had a nice formula for the magnitude of the electric field. It was the KQ over R squared type of things. And then last time we came up with a new version. But this one was only if the electric field is uniform, which is what we have if you have that parallel plate, configuration. Uniform electric field. Let me draw the little parallel plate picture. I always think that's good because this is again how I utilize this image in order to help me, conceptually determine what should happen to our energy or what kind of work do we need or this, that, or whatever. So I tend to think that this kind of picture is very important because we can't see the charges. We can't see electric fields. Now, what we can see is our little tennis ball in a gravitational field. So we can see that when the gravitational force does positive work, the gravitational potential energy decreases. And when gravity does a negative work, then the gravitational potential energy increases. And so we can use that to kind of help us out. And then I often use, this image here to kind of complete our piece. So, and the beauty here is that we have a uniform electric field in between the plates. So our E is, constant here. And then what we found was that the positive plate was the high electric potential region or the high voltage region. And the negative was the low voltage. And again, there's that funny arbitrariness to them. Let me reiterate that if there's 12 volts of potential difference between the two plates, you could have the negative plate be 0, and then the positive plate will be plus 12 volts. However, you could have the positive plate be 0, in which case the negative plate would be minus 12 volts. Again, 12 volts of difference. This one's low, this one's high. We could maybe take the 0 to be in the middle, and therefore the negative would be -6, and the positive plate would be positive 6 volts, and again, 12 volts potential difference. There's that funny arbitrariness. That's equivalent to what's the gravitational potential energy of the ball? Any number we dang well please. As long as up is positive, it's the mass of the ball times 9.80 meters per second squared times the y coordinate that we choose. And so we can make y 0, we can make it 1 meter, we can make it -2 meters, whatever. But it's the differences in the potential energies that are related to the amount of work done, either by the conservative force or by the external agents and, good stuff like that. And so for our formula here, we had that this was the charge on the positive plate over that permittivity of free space constant times the surface area of the positive plate. And like I said, if they got fancy, they write that as the sigma over epsilon naught type of things. And then what we found was you could also go in and take this as the potential difference in the electric potential divided by the plate spacing. And so then very often they'll label this as D. However, in our lab, we were using like either S or delta S or something like that. So there we go. So this is our the potential between the two plates divided by the plate spacing. Again, since this is a magnitude, it has to just be positive, and so they just do the opposite values here. And, again, we have to be somewhat cautious that a lot of times we write a potential difference as just a V, so, and I do that a lot. So that's one of the things that I tend to do. And you're going to see that in this new chapter. But so this is our new piece here, as this, potential difference divided by the spacing. And we use that to estimate the electric field in between the parallel plates on our next lab, where we took, equipotential lines and found distances between the lines at the center, and then we scooched over, and then we to the left, to the right, went up a little bit, went down. Don't go way too far, but because we expect that, in the center, in between the plates, the field should be nice and uniform. And so that's what we were trying to demonstrate. I think that since the fluctuation between the lines is going to be pretty coarse, I mean, we're probably going to be on, we're going to be good to centimeters, but not too many millimeters, and so little fluctuations in the spacing between the lines, since we only have like 2 digits in there, is going to give you pretty big fluctuations in the value for the electric field. So you shouldn't be too surprised if you end up with like a 20% difference or something like that on this one. Okay. And it has to do with numbers of digits we can reliably get for the spacing between the lines is one of those big issues. Okay. But this also implies that we get a kind of a new set of units for our electric field. They're going to be force per charge, has been what we've been using up until now, but then what we see is this could be volts per meter. And those are equivalent, and I think I showed that last time. All right, let's go in and let's do a nice little example. The example that I'd like to work is number 9 out of the text. And so what it says 2 large metal parallel plates carry opposite charges of equal magnitude. They are separated by 45.0 millimeters, and a potential difference between them is 360 volts. What is the magnitude of the electric field assumed to be uniform in the region between the plates? And what is the magnitude of the force that this field exerts on a particle with a charge of plus 2.40 nanocoulombs? All right, so we've got our parallel plates. Okay, and so we had an equal amounts of opposite charge on the plates. Creates our nice uniform electric field in between the plates. So the things I do when I draw this picture, make sure the equal numbers of plus and minus signs to indicate equal amounts of opposite charge. Try to get the spacing between my electric field lines to be pretty uniform. They should point from high to low. They should be perpendicular to this conductor and then perpendicular to that conductor. They really should go from conductor to conductor, like so, because these are equipotentials. And so then it said in the statement that they were separated by 45.0 millimeters. So that is our plate spacing. And it said that the potential difference between them is 360 volts. Okay. So then my potential difference, or just the voltage between the plates, is 360 volts, like so. With the magnitude of the field and magnitude of the force this field exerts on a particle. So we're going to put in a little particle here, and the charge on that particle is plus 2.40 nanocoulombs. 2.40 nanocoulombs. All right. So let's go in and let's calculate the magnitude of our electric field. So this is going to be that potential difference between the two plates divided by the plate spacing. And so then that's going to be our 360 volts divided by our 45.0, and then milli is 10 to the minus 3. So yeah. Okay. 8,000. I'm going to go with the new units of volts per meter, so we get used to it. And probably in terms of digits, 45.0 definitely has 3 digits. 360 is either 2 or 3, you can't tell. So the implication is that it's going to be 3, especially this is 3, that's 3, this must be 3, kind of thing is how that is generally done. So that's our magnitude of the electric field. And then they wanted to know our force. Now, which way does our force go on our little charge here? If you put it in this uniform electric field, yep. Yeah, it's going to go the same direction as the field because the charge is positive. Of course, this positive charge will be attracted to the negative plate. It will be repelled from the positive plate. So there's a couple ways to think about it. But I do like if you go back to this definition here, then we have that our electric force is the charge times the field that you put that charge into. And so if a positive scalar times a vector leaves the directions the same, so the direction of the field is the direction of the force because the charge is positive, versus if it was a negative charge, it would flip it and it would go the opposite way, the other way kind of things. And so then we can look at this plus 2.40 nanocoulombs. Yeah, we'll do 10 to the minus 9, and then we'll put in our 8,000 volts per meter. And again, the thing I had started to say was, well, the 8,000, how many digits are significant? And technically it should be 3. So probably if we wanted to be picky about it, let me just point this out. We would move it 1, 2, 3 places, and this would be 10 to the 3 volts per meter. And then the number in front of the power of the 10 should have the correct number of digits in it, significant digits. And so this gives me my 8 times 2.4. $32, carry 3, 16 and 3, 19. So 1.92. 9 and 3 is -6, but then 1 more is -5. Yeah. Newtons. And we know the direction. This is, in my image, it's to the right, but, I could have drawn the parallel plate, any old way. But we definitely know it goes towards the negative plate. So we'll put it in like that. They didn't ask for the direction. But, I mean, you can uniquely determine it. So let's go ahead and practice that. All right, there we go.